Well, I want to thank you for the opportunity to come here to Houston and give you a presentation tonight. It's always good to come here to see old friends and to catch up with what they've been working on, and of course to tell tall tales. I'm never sure when I come here if my old friends are here to visit or to heckle me, but I guess we'll find out here. Heckle, yeah, I saw that. Yeah, that's what I figured. But my talk today is an expansion of a presentation that was given at the first Australian DUG conference held in Brisbane about 2.5 years ago. The talk is designed to discuss the Proterozoic systems and also to address the dogmas associated with Proterozoic systems, and hopefully by the end of the presentation I will have convinced you that there's a lot of hydrocarbon potential in such old rocks that we're going to talk about today. In order to go back and put organic matter productivity as well as preservation and TOC content in perspective, I'm going to go back and cover about 4 billion years of Earth's history in the next 30 minutes or so. Yeah. Yeah, hold on to your hats. Time is going to fly here. But I hope by the end of my presentation that you will agree with me that there is no oil like old oil. Back in the good old days, back in the beginning of the Archean, there's only about 7.4 hours in a day. The sun's luminosity is about 72% or 73% of what it was. Now the good news was that the workday is only about 2.5 hours. The bad news was there's about 1,200 of them, so they're going to end up spending more time working during the year than they would ordinarily. But over time, the Earth's rotation did slow down, and so the length of the day started to increase. So by the end of the Proterozoic, there were about 21 hours for a day and about 416 days in a year. Now, nitrogen content continued to increase from the very beginning of the Earth's formation. Surface temperatures in the Archean were close to 70 degrees Celsius, and the ratio of methane to carbon dioxide was much less than 1. You had a very CO2-rich atmosphere. And even with that lack of oxygen in the atmosphere, you still had very intense weathering occur. And you could tell this by the presence of a carbonate mineral called nacolite. So you could tell intense weathering was taking place. Now, as time started to go forward, the surface temperatures decreased to a certain point where you could actually have life start to form. The methane to carbon dioxide ratio increased much higher. So pretty soon you had a very high methane content in the atmosphere. At some points in time, the methane content would decrease or increase enough so that you'd actually have glaciation events across the Proterozoic, and we'll talk about those in a few minutes here. This is a kind of a summary of my presentation. It's called the Proterozoic Summary. It's actually a lot of information from Craig. I published a paper in 2013. It was Marine and Petroleum Geology. If you ever want to look at the Proterozoic, go back and look at John's paper. It's a very good review of the Proterozoic systems. The scale here shows the entire Proterozoic from the Archean through the Proterozoic. And to put it in scale and perspective time-wise, here's the Phanerozoic right here. So this is how much time we're dealing with as you go forward. There's a lot of time we're going to cover here. The first fossils that were recorded occurred back here about 3.8 billion years ago in the Archaea, the methanogens, were the first life forms to evolve. Following them, about 2.47 years were the cyanobacteria. They're the ones that eventually produced enough oxygen to go back and lead to everything else we're seeing today. The oldest fossils are 3.4 billion years. They actually had, with the cyanobacteria, algal mats form between 2.9 and 2.7 billion years ago. And they actually had those in terrestrial environments, so they were pretty widespread at the time. Now, the Archean hydrocarbon deposits do have high TOC values in some places, but they're probably not very well preserved. They're not going to be significant as far as the accumulation of oil and gas that we're used to. The Paleoproterozoic here probably contains the world's oldest commercial oil and gas deposits. But as of today, there are certainly no present-day economic accumulations. But to be fair, I could say about anything. There's not very many economic accumulations we're tapping into with today's oil prices. The world's oldest hydrocarbon deposits with untapped reservoir potential are probably in the Mesoproterozoic, and those occur both in Russia and they also occur in northern Australia as well. Finally, the commercial production of Neoproterozoic hydrocarbons has occurred both in China, Oman, and possibly in Russia sometime soon. And we'll talk about those in more detail as well. Now, some of the dogmas I've heard over the years when we started looking at Proterozoic systems, the first one was Proterozoic hydrocarbons simply cannot be present and preserved in such old rocks. They just can't be there. And if you get past that point, then they come back and say, well, the organic matter could never accumulate in sufficient quantities to produce oil and gas from the Proterozoic systems. Then they come back and say, well, the rocks are probably overmature, or the hydrocarbons can't be preserved because you don't have a good seal to preserve the hydrocarbons. There's all sorts of different dogmas associated with Proterozoic exploration. And what I want to do now is go through each one of these different dogmas one by one and discuss why I think they're wrong, with the evidence we have to support why they're wrong today. First one, Proterozoic hydrocarbons simply cannot exist in such old rocks. But if you go back and you look at the worldwide systems, the areas in red right here on the continents are the exposed Proterozoic rocks. That's the surface outcrops of Proterozoic. Now obviously the subsurface extent of these rocks is much greater than what you're seeing right here. The areas with the little round dots, the yellow dots like this, are Proterozoic source rocks or hydrocarbon systems are known to be present. The stars you see around here in North America, South America, Africa, and around the world represents evaluations that demonstrate that Proterozoic hydrocarbon potential does exist, that you actually can go back and find such hydrocarbons. Australia is actually the hub for old rocks. They have Proterozoic or old rocks going back from 400 million years all the way back to like 3.8 billion years. So Australia is the hub for the old rocks like this. There have been two other areas here that have actually produced Proterozoic hydrocarbons in the Sichuan Basin. They produce natural gas. They've been doing that for some time. And also in Oman, they produced oil from Proterozoic source rocks and reservoirs. We'll come back and talk about that. The area up here in the Siberian platform, as well as this area right in here, have discovered Proterozoic reserves, but they have not yet developed them. And they have some giant condensate and gas fields up there in Russia they have never gone back to evaluate or produce so far. In my presentation, I will not talk about the Nonsuch up here in North America. There is Proterozoic hydrocarbons. They actually found some oil in an old copper mine, but their problem has been that they think Steve Yucatel did some studies on this and says that the source rocks are too lean. They're just poor quality source rocks, therefore the potential is low. I will come back and talk about the Chuar group in Utah and northern Arizona. I'll have 2 or 3 slides towards the end of my presentation to talk about that. One area I want to put your eyes on right here is up in Karelia, Russia. I'll come back and talk about this area a little bit later. The next thing, Proterozoic organic matter could never accumulate in sufficient quantities. And I hear that all the time. You simply cannot have high TOC values in such old shale source rocks. And what I want to do is go through this diagram. There's a lot of information I'm going to go through. The bottom diagram right here is some work by, I guess it was Campbell and Allen in 2008. They went back and took zircon age dates for almost 7,000 minerals across the world and plot them up here to go back and show where the supercontinents are actually formed, where they existed based on zircon age dates. And we'll come back and talk about that in a little more detail. Now, the work by Robin Kirschvink, as well as Isles in 2008, went back and used this diagram to go back and show the distribution of supercontinents over geological time. The areas in green here show the amalgamation of supercontinents. The areas in yellow show the stability of the supercontinents, and the areas of red show the fragmentation of the supercontinents. And what Campbell was trying to do is go back and demonstrate that the emergence of supercontinents had an impact on oxygen levels throughout the world, therefore by impacting organic matter content and everything else. The area in purple right here between Nuna, also called Columbia, and Rodinia, represents where you didn't have a dramatic breakup of the supercontinents. It was a little more subdued. And we'll come back and talk about this little time frame in here. So remember this little purple box right here. The continental length scale was an attempt by the authors to go back and show how far away from the equator these supercontinents actually extended. So that's what the scale is here. The only two supercontinents that actually covered in one large landmass were Nuna and Pangaea. Those are the only two that actually occurred in a larger landmass like this. The upper scale here is from Hoffman and Shroud, and they essentially showed the extent of the bacteria or prokaryotes and the eukaryote distribution, which are the organisms that actually have sterines in them. And then you actually have the metazoa, which is multicellular animals that came back in the Phanerozoic, coming back here. So this is the basic outline of what I'm going to be talking about here. There's a number of major glaciation events throughout the Proterozoic and, of course, in the Phanerozoic as well. The first glaciation took place here about 2.9 billion years ago, but it's probably a localized type of event. But this right here, they actually had a snowball Earth in the Huronian type of glaciation event. For a long period of time, there's no glaciation. Then back in the Neoproterozoic, you got another snowball event, a snowball Earth type of glaciation event. And there's always some argument as you really had a snowball Earth, you had a kind of slushy area around the equator. That's been a debate from many authors over a period of time. This right here represents the change of oxygen levels. PAL stands for present atmospheric levels of oxygen, going up to 100% here. And Campbell and Allen actually have a series of stepwise increases in oxygen. A lot of authors don't do that. Some authors actually have a decrease in oxygen right in here. The two key points you want to look at are the great oxidation events, which means that oxygen levels went from maybe 2 parts per million up to 20,000 to 200,000 parts per million. It was or 20,000 parts per million. Very large increase in oxygen right here. The second one was a global biospheric oxidation event that might have been due to the Grenville orogeny exposing continental rocks to more weathering, therefore more nutrients, therefore you have more organic matter productivity. What's interesting to me was that right before this major global oxidation event, there's a lot of sulfur, mass-independent sulfur isotope values increased. And just an observation, not saying anything significant happened, but after the GOE, everything changed. Everything changed. You had the first evaporite deposits that contained sulfate. Evaporite deposits before this time were mostly halite. There's no sulfate in them. You had the first red beds and phosphorite deposits formed right after the GOE. You had what they called the Lamongunde Getuli carbon isotopic excursion, which is the largest isotopic excursion in the Earth's history, where isotopic values, because of the burial of organic carbon, became very, very positive, some of the carbonates in the seawater. And finally, you had shungite. And the shungite deposits are 2 billion-year-old organic deposits that occur in that one area in Russia, northern Russia, that I was pointing to. In these deposits here, they're all metamorphosed now, but they represent paleo oil fields, which you had oil leaks, you had oil migrating through fissures, but these organic deposits averaged about 360 meters altogether in 9 separate beds. The thickest bed was 70 meters thick. Average TOC value was 25%, and the highest TOC value was 98%. And again, this is all 2 billion years old. We'll come back and talk about that in a little more detail. They also have a time period they call the Boring Billion. And this event actually occurs between the Huronian glaciation here and the glaciation in the Neoproterozoic. And it's where you tend to have nothing of significance happen in the Earth. In other words, you had very consistent alteration of the clay mineralogy. You had consistent organic carbon concentrations. It made it variable, but it seemed pretty consistent. There's no changes in significant changes in the atmosphere, and the oceans have stayed pretty constant, all within this time frame between these two right here. And remember, that's the time frame where they had going from Nuna to Rodinia. That's the time frame where the continental breakup was very, very gentle. So that was a Boring Billion, and according to Buick in 1995, he came back and said, never in the course of history did so little happen to so much for so long, which is why they call it the Boring Billion. But it was remarkable. Say what? Yeah, there you go. But we will see there is some variability involved here. We'll come back and talk about some of the heterogeneity, but basically compared to other periods in the Earth's history, not much was going on. So let's go back and look at the Archean, early Proterozoic oceans. The cyanobacteria did occur near the shorelines, and they produced a lot of oxygen, but this oxygen distribution was very, very localized. It was not like a widespread global oxidation event, which is why after the GOE, there tended to be very scattered oxygen concentrations here and there. But you did have, because you had oxygen up here, you tended to have the deeper banded iron formations in the deeper ocean, which is ferruginous. So you tend to have all the banded iron formations you see over in Australia were formed at this time. The deeper ocean remained anoxic. You would have a lot of productivity taking place by different types of algae, the purple, the green, and the brown algae, ranging in depths from very shallow up to 80 meters in depth. These were the main types of organisms producing oxygen and organic matter back in the Archean and early Proterozoic. If the organic matter passed through the eosinic zone, you might get consumption or get precipitation of pyrite in some cases, but by and by, most of the ocean is ferruginous in nature. What's interesting is a lot of the organic matter that's produced in these early oceans was always consumed. Most organic matter today is taken to the subsurface seafloor by attaching to fecal matter or either biogenic silica or carbonate minerals, but there's nothing living back then except for the bacteria. So most of the organic matter is actually consumed here in the water column before it could settle to the ocean floor. One gentleman by the name of Liang in 2006 suggested because the GOE occurred during a major glacial event, that maybe because there's no oxygen in the atmosphere, you had a lot of ultraviolet light striking the ice that surrounded the Earth. Therefore, you'd form hydrogen peroxide. When the ice melted, then you release oxygen. That's how they use to explain the red beds on Mars. So I'm not sure if that's true or not, but there's lots of information out there about what people think are going on. Eventually, the burial of organic matter and pyrite increased atmospheric oxygen levels. So if you think about it, if you take organic matter today, you consume oxygen in the degradation of that organic matter. By burying the organic matter, oxygen levels increase, and that's what the favored explanation for the GOE is right now, that because of the burial of a hydrocarbon or organic matter, you actually had an increase in the atmospheric oxygen levels. Everything depends on the redox reactions, and microbes are like a lot of people I know. They don't believe in working any harder than they have to. So what they do, they use the chemical process which produces most bang for the buck. The chemical process that has the biggest Gibbs free energy is the one they're going to use. So the first organisms who were out there, the methanogens, actually used carbon dioxide up here as a food source, an electron acceptor. And the change of free energy was only about 5 kilocal per mole. By the time you get to aerobic respiration in the present day, you're getting 16 times more efficient in producing ATP than you are back there. So microorganisms over time have become more and more efficient using different type of electron acceptors that go back and consume and produce organic matter. Likewise today, if you go back about efficiency of biodegradation, if you have an oxygen on the bottom of the seafloor, you're going to consume the organic matter very, very quickly. As you start going deeper and deeper, you start using other electron acceptors, and eventually you go back and use fermentation to produce the methane. All in all, the organic matter productivity increased over time. Part of that is because you put a little bit of oxygen in the atmosphere, you get more weathering, you get more nutrients, therefore organic productivity actually increases. As I mentioned, you have no biologic mineral or fecal ballasting, and most of the organic matter was consumed in the water column. But if the organic matter reached the seafloor, everything was anaerobic. There was a very high probability of that organic matter being preserved over time. And eventually, productivity dramatically increased over consumption. Therefore, you got some very high TOC values in the Proterozoic. A lot of the TOC values in the Proterozoic we will see is comparable to the Phanerozoic TOC values. If you go back and you look at the TOC values across the world, the TOC values can be very, very high. The shungite deposits here, as I mentioned, averaging TOC values 25% over 600 meters. That's very, very significant. Oman and India and Pakistan have very similar geochemistry to their Proterozoic deposits. But look at these numbers here. TOC values in Australia, there's actually some values that I think are higher than that. Brazil, Arizona, all 5, 10, 15%, 20% TOC values. So there is sufficient organic productivity in the fauna of the Proterozoic to go back and produce high ranges of total organic carbon. The next two things I want to address are that Proterozoic rocks are thermally overmature, and the hydrocarbons will never be preserved. And you're right, some of the Proterozoic systems, like the Shungite deposit, have been cooked. There's nothing left in them at all. They're essentially metamorphosed organic deposits. But there are Proterozoic systems, particularly in Australia, which are still thermally immature. The shales in some parts of Australia, Proterozoic shales, are thermally immature. They've never been cooked, because what has happened is the rocks have gone down very slowly, and they come up very slowly, and they never got cooked. They say Proterozoic hydrocarbons will not be preserved. Well, they're producing Proterozoic hydrocarbons in China. They're producing them there in Oman, and they have tremendous deposits in Russia as well. So yes, Proterozoic hydrocarbons can be preserved. And one thing to think about, if you have a source rock that's produced oil, and that oil migrates to a reservoir, it can stay in that reservoir for a long period of time. The gas can remain dissolved in that oil. But once you start to uplift that reservoir and lower the pressure, the gas will exsolve and it can migrate off to some other trap. So you can have exsolution and methane migration long time after the rock has produced oil. And finally, if you go back and you think about it, if you're dealing with a shale gas or a shale liquids play, you don't have to have the same kind of sealing mechanism as you have in conventional oil and gas deposits. Proterozoic hydrocarbons. The oldest live oil ever recorded is from the Mesoproterozoic Middle Valkyrie Formation in the MacArthur Basin in the Northern Territory. And this is a 43 API gravity oil that came from a drill stem test probably about 10 or 15 years ago. And I'll show the location of where this is in a few minutes here. One NT operator has reported flaring gas from Proterozoic shales, and they claim to have reported the first horizontal shale gas well to flow gas to the surface. And of course, this is before all the big downturn we've come through recently. If you look at Oman, they talk about over 12 billion barrels of oil being produced in some of the source rocks, and over 2 billion barrels of reserves in the Oman alone in some of the Proterozoic sections. The Huaiyang field in China, they produced at a 1.4 TCF giant field that's already produced 508 BCF of gas. Again, this is all Neoproterozoic type of rocks. They've also found some other fields nearby. I'm not going to try to pronounce that, but produced over 35 million from 3 wells so far. And once things start picking up again, I'm sure you'll see China start taking off in their Proterozoic exploration trend. And finally, I think the biggest area that has the potential is eastern Siberia. It has an undiscovered potential of 189 TCF, 16 billion barrels of oil in place, and one field alone has about 56 to 63 TCF of reserves. Again, this field was discovered back in '67. They just never have a chance to develop it yet, just based on their economy and everything else. So there is production out there. They can be preserved, and you can produce Proterozoic oil and gas. The last thing I want to cover here is the Proterozoic sediments have undergone intense tectonic deformation, which has ruptured seals, thereby limiting the ability to trap hydrocarbons. Of course, I just demonstrated you actually have production across the world, and it's true that some parts of the Proterozoic have undergone very intense deformation. But again, in Australia and Russia and in China, there's large blocks of old rock that have gone straight down and come straight back up again. If you go back and look at some of these here, here's a couple seismic lines from Australia. And you can tell by looking at these, they look like railroad tracks. They look like Phanerozoic sections for the seismic lines. This line is about 40 miles long here. This line right here is over 100 miles long. It looks like railroad tracks. And the one oil sample I talked about a few minutes ago that came from right over here, the deepest part of the MacArthur Basin here. So you do have deformation along the edges of some of these big blocks, but in the middle of the blocks, it looks like any other type of oil and gas deposit from the Phanerozoic. So I've kind of gone back and very quickly gone through and reviewed the different dogmas. I think hopefully I've shown that Proterozoic hydrocarbons can exist in old rocks. Organic matter can accumulate in large quantities, up to 25% or more in some of these areas. The rocks, some of them are thermally overmature, but a lot of them are not. Some of these rocks are actually in the oil and gas window, and there is opportunity out there.
you know, Oman's really interesting because not only is there oil in these rocks, but there's several pulses of migration that have gone through these rocks by virtue of the fact having that much time. And so what you actually see sometimes is you drill a well and you see heavy oil up here, you go through that zone and see light oil down here.
Down a little bit deeper then.
And then sometimes you move over, you see just the opposite. So this heavy oil can actually serve as a seal to some of the lighter oils below. So it's really interesting.
That's a really good point. Never thought about that before. That's a really good point. Oman has a lot of salt seals we'll come back and talk about. But you're right, the heavy oil deposit can act as a pretty good seal as well. That's a really good point. Obviously, Proterozoic hydrocarbons can be preserved. And although some of the sediments have undergone very intense tectonic deformation, some of the seals have not ruptured, and you will find the really good potential in the Proterozoic system.
I think that last point is also dependent on where the commenter has seen the tectonics and what parts of the world they've studied.
Yeah, that's exactly it too. I mean, there have been a lot of studies done recently. People kind of took a quick look at it, but they never gone back and pulled it apart to look and see what's really going on. Australia, I think, is starting to take off there now. But Australia is like it was here in the U.S. back in the 50s and 60s, large spaces with very little data to go back and explore. And it's very expensive to go up and explore. So, but there is potential. They're looking into it now. You know, that's a very good point. To go back and summarize, the Archean hydrocarbons are probably now large enough or preserved in commercial quantities. The Proterozoic are most likely to represent the world's oldest oil source rocks. And again, they may be more widely spread around, but like you said, once you get out and start looking for them, things might fall into place, and you might find more than you might expect right there. The oldest deposits with untapped commercial potential are, I think, in Australia as well as in Russia, northern Russia. We'll talk about that in a minute too. The Roper group, that's where the Valkyrie Formation is at 1.4 billion years. They have oil, I showed you a picture of. And then you have the MacArthur-Nathan groups, which are even older yet, at 1.6 billion years old. And we think there's a lot of gas and oil potential there as well. The earliest source rock for East Siberia giant oil and gas fields, 1.1 to 1.0 billion years ago. Most of the production nowadays is in the Neo-Proterozoic in Oman and in the Sichuan Basin, or South China. But there are many other countries that have this old oil potential. They include Australia, India, Pakistan, Egypt, Libya, Algeria, the Western Sahara, Morocco, Mauritania, Venezuela, and even the United States. So the potential is out there. It's just a matter of going back and having the economic incentive to go back and look for it, to explore for the oil and gas. I want to have about 2 or 3 slides and talk about the Ediacaran, that's the latest Neo-Proterozoic age, and the Chuar group there. And it was actually located in northern Arizona and extended all the way across most of western Utah right here. It was a very shallow lagoonal type deposit where you had a lot of nutrients coming off of volcanic deposits to provide nutrients for the organic matter. And the petroleum system right here, you have the source rocks down here in the Chuar group, and then you have the reservoir rock and the Tapets sandstone, and they're saying the Bright Angel shale might be the seal for this petroleum system. So this is the basic unconformity here. I think this is very close to the Grand Canyon. That's why you have the unconformity right here. If we go back and look at the section through the Chuar group, you can see how the stromatolites beds obviously indicated deposition in an intertidal type of setting. And you probably had fluctuations in the organic matter due to interglacial eustatic changes in sea level as the glaciers expanded and contracted like this here. The lowest part of the TOC values right here probably reflect an increase in nutrient supply. Little fluctuations right here, which means you had more nutrients, you had more organic matter coming forward. And they are all good source rocks here in the Chuar group. They have all the characteristics of viable source rocks. The outcrop itself is in the oil window. So you know they're throwing mature enough, at least where they've looked at them so far. And modeling by Upoff in 1997 indicated like 2.7 billion barrels of oil in place over about 150 square mile area. I think there's been one well that was drilled there. I can't think it was Amoco or somebody else. They drilled one well, They did have a little bit of gas production, but it's all carbon dioxide. So, I mean, obviously you have more work to do to go back out and take a look right there. So the increase right here, high TOC values in the upper part of the Chuar group right here, up to 6 to 8, 10% of TOC values. Thermally mature, the potential is there. It's just a matter of going back and finding the economic incentive to go back and actually look for those. Now, I want to go back and kind of summarize some of the things we've talked about here and put a kind of like a timeline of major geological events that have taken place. Again, you can see the major supercontinents up here in the upper part of the figure. But down here, I try to put in the where the abandoned iron formations would come in, where stromatolites come in, and where the metazoans actually started to take off here in the Phanerozoic. The cyanobacteria were right here in the Archean. You started having the first large source rock shungites over in here. The first sulfate and evaporite deposits, bedded evaporite deposits, actually started occurring much later after the GOE. You started to have the Northern Territory hydrocarbon generation in this time frame right here. If somebody asks you as a trivia question, what's the oldest coal deposit in the world, you can say, well, it's Proterozoic. It's up in Labrador. I'm sure it's a trivia question you get all the time. The first metazones were seen in Oman. You had the major source rocks produce oil at that point in time, and of course the first land plants occurred right in here. What's interesting to me when I was preparing their talk, they actually have an area called the Oklo area in Gabon, and they actually had naturally occurring fission take place about 2 billion years ago. Uranium was much higher, had a much higher concentration back then than it is today. And when you had a little bit of oxygen in the atmosphere, it dissolved some of the uranium from the volcanic rocks, precipitated in sandstones and conglomerates, and eventually you have water come in, and you had fission take place. And they actually have a bunch of deposits there in Africa that have naturally occurring fission. But again, if it wasn't for the water encountering some type of hydrocarbon deposit to change the redox potential, you would not have had the precipitation of uranium minerals just like you have with the roll front deposits here in Texas. I want to go back now and talk about these three areas, put some bullet points up here. The Sichuan Basin, Oman, and then the Russia area up in here. Believe it or not, they actually had gas in a well drilled in 221 BC. The Chinese drilled a well. They found natural gas and used that to go back and produce brine. By the early 1900s, the Chinese had actually drilled to over 1,000 meters looking for oil and gas using bamboo. Now, I have no idea how they use bamboo. I'm sure there's some engineer who can tell us exactly how that takes place, you know. But they actually went back and did that. But they have tremendous oil and gas deposits right there. You can go back and look at the numbers right here. Again, they had over 1.4 TCF original gas in place. They produce over half a BCF of gas so far. And so, again, it's very, very high potential right there. If you go back and look at Oman, the source rocks are Neoproterozoic to Cambrian, and the reservoirs are Proterozoic to Cretaceous, going back to what you said about all the different types of oil chemistry, how much it changed back and forth right there. They say up to 12 billion barrels of Proterozoic oil has been produced, unknown amount of gas being produced. Nearly all of it is some type of structural traps in sealed salt, and I'll add bitumen to my slide presentation for next time. And Oman, again, 8.5 billion barrels of oil, proven reserves of 5.6 billion barrels of oil, most of it Proterozoic in origin, and up to ultimate recovery of 16 billion barrels of oil. Tremendous potential for the Proterozoic in some parts of the world. Finally, go back and look at Russia. We had the Mesoproterozoic to Vendian, or the source rocks. The Vendians is the Ediacaran. That's what the Russians called that time frame. It's all formed in clastic and conglomeratic type of systems. They actually discovered the Vendian back in 1904 and 1905 at about 400 meters. They actually recognized there was potential there. The first commercial production was 1956. They discovered one giant gas field in 1987, but again, it's never been produced because they don't have the economic wherewithal to go back and do this. And since that point in time, and more recently, they've gone back and they've discovered multiple giant fields in this area. And you may have heard in the news a few years back how the Russians were going to sell a bunch of gas and oil to the Chinese. That's where it's going to come from, up in that area right in there. And finally, a lot of these areas up in Russia have a high amount of helium in the gas. And of course, as you know, helium is very, very priced pretty well right now. And I guess when the BLM gets done selling off all the U.S.'s helium, we can go back and come to them and buy it back from them or something like that. So that's a potential as well. When I first showed this slide to my wife, Donna, she turned to me and said with a little smile on her face, "Why are you sitting next to this gravestone, this tombstone?" And I said, no, that's not what I'm doing here. What this is, there's a field trip at a Hedberg conference in Beijing about 2 years ago I went to, and this is a 700 million year unconformity. There aren't too many times in a geologist's life you can go back and look at an old unconformity like that. So that's why it's not really a tombstone, it's just a marker next to the outcrop showing that unconformity. That is what I have for my presentation on the Proterozoic. I hope that I've gone through these dogmas and convinced you that some of the dogmas that people accept simply are not valid. And I hope I can convince you that there's no oil like old oil. But I think I can speak for all of us that we'll take any old oil we can possibly find. I'm not too picky about that. Thank you very much. I think the oil price is very, very important, obviously. Dick Bishop gave a presentation, Dick Bishop gave a presentation a few years, maybe a year ago, talking about they have 1 billion barrels of oil floating on the ocean. So until we go through these oil reserves we have right now, we're not going to have an incentive to go back and do this. And you also have a problem with the environmentalists coming back, talking about fracking. Some are very opposed to it, but I think the price of oil is probably the biggest incentive for going back and producing these things.
Andrew, great talk. Can you flip back to the slide that shows the Grand Canyon section?
I can do that, I think. Oop, no, I can't.
Can you do it, Lynn?
Hit escape and then
Let's do it.
You hit escape on the computer.
hit escape, you can get
Escape. Oop. Let's see here. Oh, here we go.
There you go.
You want to hear the talk backwards? Is that?
No.
Can you do that?
Oh, well, sure I can. Yeah.
And so where in there were the Chuar and
Sorry, the Chuar group is right down in this area, right in here, okay?
both of those?
And then you have the angular unconformity here, and you assume you have the migration vertically to the Tappan sandstone, and the bright oil angel shale with the seal there. Again, there's not a whole lot of information out there to go back and look for, and you have a lot of parkland and everything else, but the potential is out there. The maturity is there, the TOC is there, just like anything else, finding the right location to go to.
It'd be kind of difficult to drill a well at the bottom of the Grand Canyon, though.
Oh, no problem.
Well, that's what we use horizontal drill for somewhere else.
Are these Proterozoic oils geochemically distinct? If we have some of this stuff, do we know that's what it is?
Being back in this area here?
Anywhere?
Oh, yeah.
The White Pine, I say no. That's
The White Pines, yeah, up there in Michigan?
some other place. You know?
They have, you'd be amazed at how much information is out there using biomarkers and old oil. There's dozens of papers I've looked at out there. So they do have a very good fingerprint on the oil, particularly in Australia. But in China and other parts, in Oman in particular, they have very good fingerprints for the oil. Here, I'm not too sure about. Up in the Michigan basin, I don't know. They did find oil in that. It was a white
White Pine mine. Yeah.
White Pine mine. They found oil in that mine. I think it was a copper mine, but whether they've actually typed that oil.
Looking at today's continents?
In some cases, yes. Like I said, Pakistan, India, and Oman had similar geochemistry back with their oils, and they thought there were some similar type of things. But it's hard to reconstruct. They're getting better using the magnetism to go back and place the continent fragments. But it does help. We tried doing that in Australia to go back and place where the Northern Territory occurred, getting a feel for it.
Does Scotese not go back that far?
Say it again?
The Scotese models, did they not go back?
Oh, yeah, I can go back into my modeling back, 2 billion years ago. But it's evolving every year. They have new publications coming out.
Scottic seismic is one of the best.
Yeah. I don't know.
Is the Chuar group outcrop in the Grand Canyon the southern limit of that formation?
I think it's pretty close to it. I think it's pretty close to it. It may not be the southern limit, but I think it's one of the closest areas there.
2 years ago.
So it is the southern limit then? Okay. Hey, good guess.
Mostly in Utah.
Up in Utah up there, yeah. And how deep it is, I have no idea as far as that goes.
Yeah, the Circle Cliffs well was the Chuar way well drilled by DHT. We actually penetrated the Peace Reservoir and it did have oil staining in it, but it had been flushed by CO2.
Oh, okay.
And if I remember right, we gave some of the samples to someone at the USGS and he was reasonably confident it wasn't Precambrian source oil.
Okay. Yeah, a lot of the Precambrian, if you find the sterines, you get into eukaryotes, you're in that age range there too. So, no, going back and doing it.
Yeah, just a quick question. You mentioned Nuna and the possibility of some of these types of oils in Venezuela and Brazil, but would you expect that this system to be present along all boundaries of the continent and then the rifts when Rhodesia broke up?
I have no idea. That's a good question. I don't know. I didn't look in Venezuela and South America in much detail. Most of the area I spent was in Australia, and then looking up in China some as well. But that's a good question. I don't know.
It's clear that you want to be in an old Tectonic area to have a prayer finding this away from margins and mobile belts. Do you think that there are occurrences that we haven't found yet, say at the bottom of the Anadarko Basin or somewhere that's...
I thought you were going to say the bottom of the Grand Canyon there. That's a good question. I don't know. I mean, the deeper you go, you look at the thermal maturity trends out there, it may be all gas right now. There's a possibility. You just never know.
And as a follow-up, your upper Western Africa area there that extended, is that are you including the shale at the base of the Volta Basin?
Yeah, I don't know. I got this information from another publication, so I've not looked at that in detail, so I can't really say, yep, that's what it is.
But it does extend over just about to the coast, or the reference thought that it did?
Yeah. But I can't tell you for sure. I just don't know.
I had one last one, a really interesting thing you said, that on your timeline, you said the first coals were forming well before we had land plants.
Right.
How is that?
It was a sapropellic type of coal, so you have like little high-rich, high-organic, high-hydrogen type of masterals that would actually be like floating, and they settle out and they form a thick organic layer that got cooked. They call it a coal deposit. But you're right, terrestrial plants are coal, but they tend to go back.
Floating algal mass or something?
Yeah. They just kind of settle out like this, and they get very high TOC values, just like coal is, So, yeah.
You showed the diagram with the rotation rate slowing through time. What kinds of data or methods are used to estimate what the Earth's rotation rate used to be?
I'm sorry, I couldn't hear that. Say it again?
You showed how Earth's rotation rate slowed through time. It's slower now than it used to be in the Proterozoic.
Mm-hmm.
What are the data and methods that are used to derive those estimates of previous rotation?
I have a stack of about 3 or 4 references I can give to you. I'll give you the reference numbers for them. But they were coming out. There's the one was called the faint sun. There's a paper talking about that. There's 2 other ones too. One guy from the Middle East had a paper on it as well. I think I had 2 or 3 references I went back and I was able to put that together and put in an Excel spreadsheet and kind of calculate what it is as well. But let me know. I'll give you the references for that.
And the tides at that time were horrendous because the moon is so close, and that as angular momentum got transferred to the moon, it orbited out farther, and so that's why things calmed down. You can imagine the tides at that time.
Oh yeah,
Wow.
yeah. I think the moon was like 25% bigger in the sky or something like that. It was much closer, much bigger.
Also, you can see, if you look at the sediments closely, you can see rhythmites in there that
Yeah, we saw those.
Information and how long the days were and so forth.
Yeah, we saw some of those last year out in Utah.
We
They
see
took us
that
out.
even in Colorado.
Oh, yeah, okay. That's amazing. That's amazing.
Okay, I think if any other of you people have questions, come up and Andrew will answer them for you. Right now, I'd like to give you the Speaker's Award here, which is Rattlesnake Limestone. Real
Oh,
pretty.
great, thank you very much, I appreciate it. Thank you for your time.